go. And we're going to get into topic 4, which is our final production. And this first section is on properties of materials. So when you're designing a product, you're going to make it out of something. And depending on what you want your product to do, that's going to determine what you're going to make it out of. So you can see this little chart on the top right. We're basically comparing lots of different types of materials. And right here, they're being compared based on their density. So whether something is lighter per unit volume or heavier per unit volume, and Young's modulus, which really is looking at the stiffness or the flexibility of a material. Okay, so you see woods, foams, rubber, polymers, ceramics, metals, alloys, and composites are all on here. So we'll talk about a lot of those. This is a big lesson, and then it's going to get into smaller lessons that focus on each of the different types of materials. Okay, so materials, they're selected based on their based primarily on their properties, like we just talked about. Scientific discovery and new technologies have had a major impact on material science. Designers have more materials from which to choose from, which allows for smart new products and the enhancement of classic designs. Choosing the right material is a complex and difficult task. You have to consider things like their physical characteristics, the aesthetics, the mechanical characteristics or qualities, environmental qualities, and the moral and ethical issues surrounding different materials. Physical properties include things like the weight. Really, you should say the density, but it would be weight if you have a defined volume. Volume, density, electrical resistivity or conductivity, thermal conductivity or resistivity, thermal expansion, and the hardness, which is the resistance to scratching. Mechanical properties that you're probably going to want to consider are your tensile and compressive strength, stiffness, toughness, hardness, ductility, elasticity, plasticity, Young's modulus, and stress and strain. When we're talking about aesthetic characteristics, it's basically how do the senses interact with the product? So examples of where that might be important would be appearance, taste, odor, flavor, texture, and sound. Stress and strain graphs. IB says you might use them to identify appropriate materials. I threw a couple charts on here so you can see what a stress and strain graph really looks like. So the little pig, kind of big pig, standing on that diving board is applying a stress to the diving board. The strain is the amount of the change or the displacement of the diving board. So when we look at a chart like what's on the bottom left here, stress is this left side. It is the load that's being applied. Strain is the deformation or change in placement. And what you get, this slope right here, is your stiffness. So the stiffer a material is, the more vertical that slope is going to be. The less stiff or flexible it becomes, the flatter that slope is going to be. Now at some point, it's going to go from its elastic region, and elastic means it'll stretch and then go back to its original shape or size. Once you get into this red area, you're now into what's called the non-elastic or the plastic phase, which means it has permanent deformation to it. And at some point, it's going to fail. So if this pig was heavy enough, he could cause this diving board to bend to the point where it's never going to go back to what it was before, a flat diving board. And if he got even heavier, eventually the diving board's going to break, and that would be the failure point. Okay. Same thing over here. Feel free to pause this and you can read through these 4 scenarios of what would happen with the stress and strain curve. Smart materials are likely to be developed in specific regions or countries. Their benefits may be limited globally. New materials, often developed by material engineers to have specific properties. There are engineers that are specialists just on materials. That's all they do all day long is test and learn about new materials and think about how can we possibly make even newer stuff. Allow designers to create new products, solving old problems in new ways. The explosion of the plastic materials following the Second World War enabled products to be made without using valuable metals, because we can now make them out of plastic. Physical properties. Density, important in the relation between the product's weight and size. For portability, if it's too big and heavy, you're not going to be able to haul it around very easily like your phone. Prepackaged food is sold in weight or volume. Electrical resistivity, particularly important in selecting materials as conductors or insulators. If you have any kind of electronics going on in your device, that's going to be really important. There are certain times you want the electricity to flow and certain times you certainly don't want it to flow. Physical properties. Thermal conductivity, important for objects, so it will be heated and must conduct or be insulated against the heat gain or loss. Thermal expansion or expansivity, important where two dissimilar materials are joined because they don't expand at the same rate, which can cause them to break. Hardness, important where resistance or to penetration or scratching is required, like a ceramic floor tile. They have to be extremely hard and resistant to scratching. Diamonds are considered like the hardest thing on the planet. So you see your floor tiles in this person's kitchen. You would not want those to scratch easily. You can see this bridge, and you guys have all seen these before in your real life, and you may never have thought about it. The way these pieces interlock, it allows the bridge to expand and contract as it gets warmer and cooler. That way, the bridge isn't buckling. Mechanical properties. Tensile strength is important for ropes and cables, like an elevator or a suspension bridge. Stiffness, important where you want to maintain a shape when that's crucial to performance, like aircraft wings. Now, we would say aircraft wings are pretty stiff, but at the same time, they actually have the ability to flex quite a bit, which is a good thing because we don't want them just breaking off. Toughness, important where abrasion and cutting may take place. Ductility, important when materials are to be extruded. Okay, that's when we make wires. We tend to warm metal and then we extrude it because it can be rather ductile. Aesthetic characteristics. Some aesthetic characteristics are only relevant to food. Although these properties activate people's senses, responses to them vary from one individual to another. Difficult to quantify scientifically. Piezoelectric material. This is a smart material. And if you're not familiar with piezoelectric materials, it's a crystal. And I'll read through this and I'll explain a little bit more. When deformed, it gives off a small electrical discharge. When an electrical current is passed through it, it increases in size, up to 4% of its volume. Widely used as sensors in different environments, can be used to measure the force of an impact on a car, and sends an electrical charge that activates the airbag. So in the sides around the perimeter of your car, you have little piezoelectric sensors. They're little crystals. And if your car gets hit, it's going to compress that crystal. And the compression of that crystal is going to release an electrical discharge. The electrical discharge is then going to go to this crash sensor, which is going to activate the inflator and deploy your airbag. So piezoelectric sensors are used in your daily life. Shape memory alloys. These are another smart material. Shape memory alloys are metals that exhibit pseudo-elasticity and shape memory effect due to the arrangement of their molecules in the material. The shape memory effect allows severe deformation of a material, which can then be returned to its original shape by heating. Examples: eyeglass frames, medical tools, antennas for mobile phones, and space solar arrays. I'm going to give an example with the space solar array. They're going to create the array the way they want it to be. They're going to then compress it down, fold it up, compress it down into what it needs to be on a rocket to get put up into space in orbit. And once it gets there, let's say on the International Space Station, when you put it out and it's exposed to the sunlight, it will then heat and expand back to its original shape. Shape memory alloys, again, smart materials. For robotic limbs, hands, arms, legs. Difficult to replicate even the small movements of a human body. The gripping force required to handle different objects like eggs, pens, and tools is very difficult for us when we're talking about prosthetics. These shape memory alloys, which are smart materials, can allow us to do this in better ways. Can be used to create smooth, lifelike movements. Computer control of timing and size of the electric current running through the shape memory alloys can control the movement of an artificial joint. Photochromicity. Photochromicity. This is going to be the changing of color or darkness with exposure to light. So reversible change of color when exposed to light, color changing sunglass lenses, which can darken as the sun brightens. A chemical either on the surface of the lens or embedded into the glass reacts with the ultraviolet light, which causes it to change form and therefore its light absorption spectra. Electrorheostatic and magnetorheostatic. ER and MR materials are fluids that can change in their viscosity. They can change from a thick fluid to a solid in a fraction of a second. Magnetic materials are used for car shock absorbers, dampening washing machine vibrations, prosthetic limbs, and exercise equipment. Electric, ER, electrorheostatic, used for clutches and valves, engine mounts, designed to reduce noise and vibrations in vehicles. Thermoelectricity. At its simplest form is electricity produced directly from heat. It involves the joining of two dissimilar conductors that, when heated, produce a direct current. Thermoelectric circuits have been used in remote areas and space probes to power radio transmitters and receivers. So you have two different materials, maybe one on the top and one on the bottom. When they are heated or cooled, those two different materials can create an electrical flow. So the electrons are actually flowing through them because of their properties. And that's electricity. If electrons are flowing, you have electricity. It's not a ton, but it'd be enough to power some things. And that's it.